This is going to be a tutorial for the 2.0 release of the Hierarchical Independent Component Analysis Toolbox, also known as HINT. So this is a toolbox for doing independent component analysis of functional magnetic resonance imaging data when you have multiple different subjects and you are interested in understanding how different covariates may be related to changes in their brain networks. With the 2.0 release, the HINT toolbox is capable not only of doing cross-sectional studies, but also of longitudinal studies, so repeated measurements on subjects over time. And so this tutorial is going to be split into two parts. The first part is going to correspond to using the HINT toolbox to carry out an analysis of cross-sectional data. And the second part is going to be using the HINT toolbox to do an analysis of longitudinal data. To use the HINT toolbox, the first thing you'll need to do is to download the MATLAB package, which is available on the CVIS GitHub page, seen here. And I'll include a link to this in the video description. So this is just the main page for the HINT toolbox that will be updated with the 2.0 release version. To download the toolbox, just come over here to the code button, click on it, and select Download Zip. And this will download a zip file containing the HINT toolbox. Once you open up the HINT toolbox folder, you should see something like this right here. And so the first thing we're going to want to do is actually generate some data to use as an example. So if you look at the side folders here, there will be one called test. And if you open that up, you can open up this generate test data MATLAB file. And so what this is going to do is it's going to generate a cross-sectional data set and a longitudinal data set for us to use as the examples. And so I'm going to go ahead and click on Run here. And that will generate this test data. So you can see when I clicked on the button there, a new folder was created called test data. And right now it is being generated and placed in there. And if you want to disable that or delete that at a later time, you can open up this cleanup test data file and run that. So while that's generating, I'm just going to talk real quickly about what that data actually look like. So we're giving these data sets names just as an example, but of course these are just simulated data. So first, for the cross-sectional analysis, we're calling this an Alzheimer's disease data set. And so this is just an illustration with 30 different subjects, each having a single visit. And we're going to have two different covariates of interest for our analysis. So the first is going to be age, which we're going to have ranging from 50 to 80. And the second is going to be diagnosis, which is either going to be Alzheimer's disease or healthy controls. And so just a small detail here, all of these simulation data were generated using population level maps obtained in previous studies. And we're going to generate the covariate effects by taking regions of interest within those population level maps. So for example, we have a frontal parietal right network here. And so we can see what the population average looked like. So this is going to be our population level map. And then we've placed an Alzheimer's disease effect sort of in this frontal region and a age effect in this rear region. And then we've got the Alzheimer's disease by age interaction, and that's going to take place sort of in this frontal region, but more away from the center. So for all three of these images, the blue is going to correspond to places where there is an active covariate effect. Similarly, while this data is generating, we're also going to be generating a longitudinal data set. And so this data we're going to be calling the medication data. This is going to be similar to the cross-sectional case. It's just illustrative simulation data. And so we're going to have three different covariates here that we're going to look at their effects on the brain network. The first is going to be a treatment covariate with 3 levels. Those levels are going to be no treatment, traditional treatment, and a novel treatment. And there's going to be an age-related covariate and a medication type covariate. And this medication type is going to have 3 different classes: powder, injection, and capsule. And so once again, the actual effects themselves are going to be nestled within population level maps. So on the left here, we have an example of what the population level default mode simulation brain is going to look like. And here on the right, you can see the age effect in green in the posterior cingulate region, and then a more lateral treatment effect here. Once the data have finished generating, you'll be able to find them in the test subdirectory of your HINT folder. So under test, you'll see a folder called test data. And if you expand this, you'll see your Alzheimer's disease data set, as well as the medication data set. So everything that we're going to need for this tutorial can be found in one of these two folders. One other thing, if you're following along and you run the script and you do the Alzheimer's disease and medication analyses, and then later you want to get rid of those files, you can open up this cleanup test data MATLAB script. And if you run this, it'll get rid of those two data files for you. Now that we've covered the data generation, we can go ahead and take a quick tour of the hint toolbox. So to open up the toolbox itself, or the toolbox's GUI, you're going to come to this hint.m file, which is at the top level of the hint toolbox folder. And you can just go ahead and click run, and that will open up the toolbox. The hint toolbox is split into three main panels. The first panel is the prepare analysis panel. So this is where you're going to do most of the work involved with setting up the analysis, specifying the model that you're interested in, doing pre-processing for the imaging data, generating an initial guess for the EM algorithm, and then doing some sanity check of your population level components. And so we're going to go through each step of this prepare analysis panel in just a second. The second panel is the run analysis panel. And so this is where you're going to set up the parameters for the EM algorithm and estimate the model parameters for the HCICA model. And then the final panel is going to be the visualization panel. And so this is the panel that you're going to use to open up our brain visualization toolbox. And so this is what's going to let you do things like look at the different population level maps, look at the different covariate effects, and do things like testing contrasts between groups. So we're now ready to start a cross-sectional analysis. This is going to be our Alzheimer's disease simulation data. The first thing that we need to do is set up an analysis folder. This is going to be the folder where Hint is going to place all of the output from the analysis, as well as all the intermediate files, so things like the initial guess and some of the pre-processed data. So to set this up, we can click on the Browse button. This is going to open up a file selector window. And I'm just going to go to my desktop and I'm going to create a folder here for this. So I'm going to create a new folder and I'm going to call this tutorial Alzheimer's. And I'm going to click on open. So once that's done, you should see the analysis folder will fill out in the text box here, and then we're ready to move on to the data input. For the second part of the analysis preparation panel, we're going to need to tell the hint toolbox where our Nifty data is and what type of data that we want to read in. So for this, we're going to click on the Import Nifty Data button, and then we're going to come down here and select Load Data. This is going to open up a second panel that's going to ask us just some basic information about the data. And this is also where we're going to specify whether we're looking at a cross-sectional analysis or a longitudinal analysis. For the Alzheimer's disease simulation data, this is going to be cross-sectional, so we can just leave this as is. The next thing we need to specify is the mask for the analysis. So we can come down here and click on Select Mask, and then we need to navigate to where this mask is stored. So if you remember, for us, this is under the test folder, test data. We've got our Alzheimer's disease data set here. And so if I scroll down past all the subject data, at the very end here, there is an Alzheimer's mask. So I'm just going to click on that and select Open, and this should automatically fill out. The second thing that we need to do is input the covariate file. So I'm going to go ahead and click on this and upload it, and then I'll show you sort of how the covariate file needs to be structured for the analysis. So if we click on Select Covariate File, once again, looking at that same sort of file tree here, there's a CSV file labeled Alzheimer's covariates. Just go ahead and select that and click on Open. It's going to read it for a second and make sure everything is valid. And then it's going to open up this input summary. And this is going to let you know if any of the Nifty files appear to be missing or duplicated. So I'm going to click on Continue here. And then I'll click on OK. And if everything's worked out all right, this load data progress bar at the bottom should fill out. So you may have noticed that in the data input before, the toolbox was able to figure out where all of the Nifty files were without us explicitly pointing it to them. This has to do with the way that we insist on the covariate file being set up. And so I'm going to show you what that looks like now. So I've navigated to the Alzheimer's disease folder from my file explorer, and I'm just going to double click on the CSV file for the Alzheimer's covariates. Just going to give that a second to open up here. So you can see what this looks like. So this is just a very simple CSV file. And the important thing here is that the first column of the CSV file needs to be a column containing the file paths to the Nifty files for every subject in your analysis. And so this is just an easy way both to read in the data and to make sure that the subject level data is properly aligned to the corresponding covariates. So the first column is going to be the file path for each subject, and then the remaining columns are going to be the covariates that you are interested in. And it's okay for you to have extra columns here corresponding to covariates that you don't actually want to include in the analysis. And I'll show you in just a second how we deal with that. But for now, you can see that both of our covariates of interest are here. So we have age in one column and group in the other. One other thing that I want to point out is that you don't need to worry about coding your categorical covariates ahead of time. So you can see within group here, we have labels as healthy controls and AD, which is for Alzheimer's disease. And we'll worry about applying a coding scheme to that within the toolbox in just a second. So before I move on to talking about the model specification, I want to talk just a little bit about how the hierarchical ICA model actually works. So at a very high level, the HCICA model for a cross-sectional study is a two-level hierarchical model. The first level of the model is actually just a sort of standard noisy spatial ICA model. And so this is going to take the observed data for any given subject after pre-processing and write it as a noisy ICA model. So the brain networks are going to be the spatial components, and the mixing matrix is going to give you how those components combine to generate the observed data, plus some error. Now, the second level is where we need to really think about the model specification. So in the second level of the hierarchical ICA approach, we write these participant-specific spatial components, so these subject-level brain networks, as a linear combination of a set of shared components and a set of covariate effects. And so basically, you can think of these shared components as being like the population-level network. So this would be things like the default mode network or the visual network that you're probably already very familiar with. And then these covariate effects are going to capture how different things, like age or Alzheimer's disease, are associated with changes from this sort of baseline population level network. And so what this looks like is the following equation. So we have that SIV, so this is the subject level brain network at voxel V, can be written as a population level component plus a set of covariate effects. And so these covariates are going to be captured in this X variable right here. And so within the HCICA approach and within the hint toolbox, what we need to do is we need to take the covariates that you've input and we need to create our corresponding X from these. We're going to do this using the model specification button. So if we come within the hint toolbox down here after inputting the data, we can click on model specification. This is going to open up another window for us. And so this window has several different parts. Across the top here, we're going to see the model matrix for the HCICA analysis. So you'll notice a couple of things here. First, age is no longer the raw values. So we've centered and scaled age, basically a Z transformation. And similarly, you'll see that the disease status has been automatically changed from the raw values, which said healthy control or Alzheimer's disease, into an effects coded variable. So you can see that we have -1s and 1s. At the bottom of the panel, you'll see that we have several different subpanels. So the first here is going to be the model specification. This is going to let us control what covariates are actually included in the model. So for example, we might not want to include the Alzheimer's disease group or a healthy control group indicator. Instead, we might just want to model with age. And so we can easily do this by taking the covariate in the model and clicking remove, and you'll see that the model matrix automatically updates to reflect this change. Similarly, we can add it back in just by highlighting it and clicking on add. The next subpanel is going to let us select which type of covariate each thing is. So covariates with strings like HC or AD will automatically be converted to categorical covariates. But sometimes you might already have a categorical covariate that you've given some numeric coding. So for example, it's very possible that in your covariate file, you may have coded healthy controls as 1s and Alzheimer's disease patients as 2s. And so to handle that, we have this right here, which will let you automatically, or will let you tell Hint to consider a numeric covariate categorical. And so I can do this, for example, with age. I can highlight it and click on Make Categorical. Obviously, this is a pretty bad idea, but you can see that this has now taken age and it has created a separate category for every age value observed in the data set. But obviously, we don't want to do it this way. So I'm just going to click on age here, and I'm going to click on Make Continuous to sort of revert that change back to what we had before. Another thing we can do is set what the reference category for each covariate, each categorical covariate is going to be. So within group right now, our reference category is the healthy control subjects. And so you can think of this like the -1 category within the effects coding. But if for some reason I wanted to change this to be the Alzheimer's disease patients, I could just come over here and instead of healthy controls, could change this to Alzheimer's disease. And so you can see now the corresponding column of the model matrix has changed to reflect that. But I'm going to change this back to healthy controls as our reference category. The next panel will let us specify interactions in the model. So as I mentioned when we were first creating this data set, we want to include an interaction between age and disease status. So I'm just going to come down here and I'm going to select group and add interaction. This will let us add different interactions into the model. Similarly, if we want to remove an interaction, we can just fill out the corresponding interaction and click on remove. But I'm going to add that back in. The final thing within this window is an option to scale continuous covariates to have unit variance. So I mentioned earlier that we were doing a Z transformation of the age covariate. If for some reason you don't want to do that, you can just uncheck this box. And so you can see now age has reverted back to the original values, the original centered values, and we have the corresponding interaction has also updated to reflect this change. Now that we've finished the model specification, we're ready to start pre-processing the data and generating an initial guess. So the first thing we need to do is specify the number of principal components that we want to use for this initial guess procedure. As a general recommendation, we suggest doing at least 2 times the number of independent components, but you can go higher if you have reason to believe that a larger number of principal components are needed. So for this analysis, I'm planning to use 3 different ICs. And so for the number of principal components, I'm just going to double that to 6. Then I'm going to fill out the number of ICs as 3. And the rest of this is very simple. So we'll just press PCA dimension reduction. You should see the MATLAB command windows start to fill out with some output. Basically, this is going through and this is doing a PCA on every subject's data separately. And then this PCA reduced data is going to be stacked along the time domain, reduced again, and then in the initial guess procedure, we're going to do an ICA on the stacked data. And so the point of this is just to get us a reasonable set of starting values for the EM algorithm. This PCA dimension reduction step can take a few minutes, especially if you've got a large number of subjects. And so I'm going to pause the video now and I'm going to wait for it to finish. It's a couple minutes later now, and you can see that the progress bar has now highlighted the PCA step, which means that that pre-processing procedure is now done. The only thing that's left for us to do before we can start the actual EM algorithm is that we need to generate a set of initial values for the EM algorithm. So this is just going to take the output from that PCA dimension reduction, run a standard spatial ICA on it, and do some rough estimates just to give us a good starting position for the EM algorithm. If we come over here and click on Generate Initial Values, we can see that now the progress bar has filled out all the way, and we are ready to preview our population level components. And so the reason for previewing these components is just to make sure that something reasonable has come out of our initial guess procedure, because we don't want to start the EM algorithm with a very poor set of initial values. So if we click on the Preview Population Level Components button, the viewer window will open up. And so there's a lot of different pieces to this viewer, and we're going to go a lot more into detail on it sort of after we have done the EM algorithm analysis. So for now, I just want to point out that on the right-hand side, we have a viewer that is showing us the brain and some of the estimated guesses for the components. And we can click on this viewer to navigate to different parts of the brain. And so here you can see what is clearly a default mode network. This is going to be our initial guess for the population level default mode. I'm going to come over here and I'm going to move from this first component to the second component. And you can see if I click up here now, clearly this is one of our frontal parietal networks. And then if I shift down here to the third component, it will automatically update and show us the last one here, which looks to be a visual network. So having looked at the true values of the data when we generated it earlier, we know that this is very reasonable. And this looks very much like the standard sort of population level networks that we would expect to see. And so we're pretty satisfied with our initial guess. We can just come up here and click on X to close the viewer window. You can see that the preview part of the progress bar has filled out, and we are now ready to move on from the first panel to the actual estimation procedure. So we'll click on Save Setup and Continue, and that's going to ask us to input a prefix for the analysis. So this prefix is going to create a subfolder that's going to store all of the results for the analysis. So I'm going to call this interaction because we've included an interaction term in this model. And then I'll click on OK. And it's just going to take our setup here and it's going to save it to that output folder from earlier. To see what this looks like, I've opened up the tutorial Alzheimer's folder that we specified as the output directory. You can see there's 3 nifty files here, each of these corresponding to one of those population level networks that we looked at earlier. And now there's a new subfolder here called interaction results. It says interaction is the name of the prefix we came up with. And within this folder, you'll see a interaction runinfo.mat file. So this is a .mat file that's going to contain everything that we need for the analysis. So things like the covariate model matrix, the initial values, and then a lot of just general parameters about the analysis. So now we're in the second panel of the toolbox. This panel is going to be where we are going to estimate the model parameters using the EM algorithm. There's 3 different settings in this panel. The first is the maximum number of iterations. This is the maximum number of iterations before the EM algorithm will terminate regardless of the convergence status. We usually just use 100 here. The second and third parameters are epsilon terms. And so these are convergence rules for the global and local parameters. So the global parameters is going to refer to everything in the model except for the covariate effects. So this is things like variance estimates and population level network parameter estimates. And then the local parameter is going to correspond to the covariate effect parameters. And so once the relative change from iteration to iteration has fallen below these 2 values, the algorithm will terminate early. Usually we use a smaller value for the global parameter than the local parameter because we tend to see a little more change in the local parameter from iteration to iteration. So once those 3 things are filled out, we can go ahead and come down here and press run, and then the algorithm will start running. As the algorithm runs, we'll be able to see the change from iteration to iteration in our global and local parameters in the corresponding plots here. And so we can also use these to monitor convergence. And so sometimes with the EM algorithm, what we'll see is that it levels out at a certain point, but that certain point is below the or above the convergence threshold that we set. And so in those cases, we could just go ahead and come down here and click on stop to terminate the algorithm early. But I'm going to let it finish running. The algorithm is now done running, and we have finished estimating the parameter values. You can see that the analysis status has moved to 100%, and the display results button is now enabled. Before we actually go take a look at the results, let me show you what the output folder should look like. So here is our interactions result folder that we created earlier. If I expand this, you can see this is now full of nifty files. So we have the aggregate ICs, which are looking at sort of the sum of the component across all subjects. We have the covariate effect estimates. We have variance estimates for those covariate effects. And then we have the population level maps, which are labeled as the S0 maps. And so we're going to be able to take a look at all of these things a little bit more in the next panel. We can move to the next panel once we're done looking at the run analysis panel by clicking on the display results button. This will take us to the visualization panel, and you can see that the display path is already filled out for us, as is the prefix. So this gives us some idea of why we wanted to use the prefix in the first place. So if we were to run several different analyses, say maybe slightly changing up the covariate effect model that we were looking at, adding interactions, removing interactions, that type of thing, we can give all of those unique prefixes, and then we'll be able to select them from the drop-down menu while keeping them all within the same folder. Once we're ready to actually open up the viewer window, we can come down here and click on Display. This is going to open up the viewer window that we saw earlier. And so now I'm going to go through and show you sort of what each section of this window contains in it. So first, all the way to the right is the main thing that we're interested in, of course, which is going to be the brain. So this is going to show 3 different views of the brain. And just like we saw with the initial guess earlier, we can click on these views in different locations to navigate to that voxel. We can also slide through these one slice at a time using the slider bars here at the bottom. And so you can see as I click on these, we move forward and backwards in the brain. The right-hand side here is going to be a color bar showing us the intensity values of the map at each voxel. And we can also see the exact intensity in the text box right here. We can change color maps using this drop-down menu right here. Right now we have 2 default color maps. One is the JET map, and the other is the Parula map. So you can see we can switch between those maps using this drop-down menu. We can also change the range of the color bar using this color range option. So for example, here we can see this is sort of maybe a little bit too narrow of a range here, going from -2 to 2. We can see that that maximum of 2 is sort of being hit by a lot of the values in this map. So I can change this, say, to 4, and you can see that the color map changes to respect that. There's a plus and minus button here, which we'll come to a little bit more in a second, but basically this is going to let us add and remove additional views of the brain. So for example, if I click plus here, you can see now we've got 2 different brain views going on. And so we can use this to sort of look at several different aspects of the brain networks at the same time. We'll come more to that later. For now, I'm going to get rid of this by pressing the minus sign. This will revert us back to just looking at this single brain view. So then one of the more important subpanels here is going to be this image subpanel. This is going to let us control what we're looking at. So right now we're looking at the population level maps. Other options involve specific subpopulations, specific covariate effects, different linear combinations of the covariate effects, and then single subject maps. And so I'm going to talk a little bit more about each of those in just a minute. Another thing that we're going to be able to do using the viewer is to create masks. And so we'll be able to threshold these different maps at different values and output and or apply masks based on these values. And so we can use those masks within Hint, but you'll also be able to take those masks and use them in other software like FSL, maybe to apply them to different data that you have. The third panel here is going to be created for each different brain view that we're looking at. And this is going to let us do things like sync the different viewer windows, sync the different ICs that we're looking at, sync thresholding, and so on. And so we're going to get a little bit more into that in just a minute. Next, we have a thresholding subpanel. So this is what we're going to use to threshold the brain at different levels. And so you can see if I grab this slider bar and drag it, the brain is being thresholded as we go. Similarly, I can lower that back to 0. And then we can do the same thing using the text input. So say we wanted to threshold this at 1.64, we can just type that in and press enter, and it will go ahead and jump to that threshold level for us. Finally, all the way to the left here, we're going to have some different, more specific features of the viewer window. So we're going to have this top left panel here, which is going to let us do subpopulation selection. And so we'll explore that more in just a minute. We can also change this over and we can look at specific linear combinations of the covariate effect values. And again, we'll look at that a little bit more in just a minute. And then finally, there is a trajectory viewer, and this is exclusive to the longitudinal data analyses. So next, let's look at some of the things that we can do using the population level network maps. So the first thing I want to do is draw the crosshair so that I can see where I'm clicking just a little bit more clearly. So if we come down here to this box, we can check the draw crosshair, and you can see that now whenever we click somewhere in the brain, there is a crosshair on the screen that sort of tracks where our current voxel location is. Now, one of the most common things that we'll want to do with the population level network is construct some sort of mask. And so this mask is going to sort of create a 0-1 rule for saying what voxels do and don't belong to the network. So the first thing that we're going to want to do is convert these images to z-scores so that the intensities are sort of normalized across different networks in the brain. So I'm going to click on View Z-scores, and you can see that the values have all changed a little bit to reflect the standardization process. Now, let's apply a threshold of 1.64. I can come down here to this box, and I can input 1.64 and hit Enter. And we can see that most of the voxels in the brain have been wiped out from the mask, but the pieces belonging to the posterior cingulate, these two lateral regions, and the frontal region have survived. So this would be sort of our default mode network mask. And so you can see it a little bit better, say right here. So I can save this mask by coming over here and clicking on Save Mask. So when I click this, it's going to ask me what I want the name for the mask to be. I'm going to say default mode network, and I'm going to click on OK. And so this will write out a nifty mask, a nifty binary mask to that same output directory that we created earlier. If I get rid of the thresholding, I can also now apply this mask by coming over here to this drop-down menu, and you can see that that mask I created has automatically been added to our list of available masks. I can click on it, and you can see that it has been applied. So that's how you create masks. Another thing we'll likely want to do is look at several of the different population level networks at once to sort of compare the spatial regions that are active within each of these networks. So this is a good use for that plus and minus button that we saw down here earlier that are going to let us open up more viewers. We did an analysis with 3 different ICs, so I'm going to go ahead and open up 2 more viewers so that we have a grand total of 3 that we're looking at. So you can see all of the changes that we made a second ago, like changing to z-scores and drawing the crosshair, are all applied to this top level brain view, but not the bottom 2. So the first thing I'm going to do is change the second view to be the second component and the third view to be the third component. And then I'm just going to click around in the brain a little bit to try to find the different regions here. So we can see here's our frontal parietal network. Here's our visual network. And so now we've got a view of all 3 of these. We can also apply the mask that we created earlier for the default mode to these other brain views. I'm not sure why we'd want to do that, but we can grab the mask here and apply it. And so you can see we've sort of applied the default mode network mask to this frontal parietal network. So I'm going to go ahead and convert both of these to z-scores. And one thing we might want to do when we're looking at several different networks simultaneously is sync them up so that we're always looking at the same voxel. So we can do this within the brain view selection boxes down here. So I'm going to leave the first view as free selection. But for the second one, I'm going to select sync, and I'm going to sync it to brain view 1. And similarly for the third one, I'm going to select sync and also sync it to brain view 1. I'm also going to go ahead and sync up the color maps using this button here, and I'm going to sync up the thresholds. So this means that any thresholding we apply will be applied to all 3 maps at the same time. So now if I click somewhere in the first brain view, you can see that it will jump to that same location for both of the other 2 views. So again, I can maybe click over here, and we'll see that all 3 of the brain maps, after a slight delay, jump to reflect that. Similarly, if I want to apply some thresholding now, I can use a threshold of 1, and I can input that here. And after waiting for a moment, we'll see that all three maps are going to update to reflect that the threshold that we've set here. So this gives us a way to look at several different maps at the same time and apply similar sorts of transformations to them. One of the main things we're interested in doing with the hint toolbox is looking for locations in the brain network that there are differences in the brain network associated with various covariate effects. And so we're going to focus on how we can examine that next. So I've gone ahead and switched this main viewer to be the second IC. So this is going to be that frontal parietal component that we were looking at earlier. I'm going to go ahead and add another brain viewer down here. And I'm going to take this brain viewer and I'm going to sync it to the first one. So I'm going to select sync selection. I'm going to sync it to brain view 1. And I'm going to go ahead and sync the components that we're looking at. And I'm going to sync the color map values. I'm also going to go ahead and switch it to z-scores. I can then come over here, and instead of looking at the population level network, I can change this to be covariate effects. And so this is going to let us look at the estimates for each of our covariate effects. You can see that the IC is currently locked to IC2. This is because I have this Sync ICs button selected. And a new drop-down menu has appeared that lets us choose between age, group, and the interaction between age and group. So to demonstrate how we might do model-based hypothesis testing here, we've already converted these images to z-scores. So this conversion is going to be done using the variance estimator from the HCICA model. So regions in this map above a certain threshold correspond to what would survive hypothesis testing at that threshold. So I can come down here and I can actually input a threshold, let's say 1.64, and we can see which voxels would survive. And so we can see that the estimated age effects, we have a very large contiguous effect within this parietal region here. And so just like we saw earlier, that is the region that we actually included the true covariate effect. So this is where we are finding a significant age effect in the brain. Similarly, I can come over here and change from age to Alzheimer's disease group. And again, we can see a strong effect, but this time located within that frontal region, just like we saw when we generated the data. So this is an example of how we would look for different covariate effects within the brain. Another thing we might want to do is take the covariate effects that we have now thresholded and output some Nifty file with the resulting values. And this might be to do something like open it up in another viewing window or saving it for submission with a paper and so on. So we can do this using the export function at the top of the GUI. So I can click on export and this save to .nii. This is going to open up a Nifty file exporter. I'm going to tell it that I want to save brain view 2. And I'm going to tell it to output the brain map. And so that's going to be this right here. Another option would be the p-value maps or the -log p-value maps. And so for this input file name, I'm going to say AD effect, and then I'm going to click on save. Now, if I open up the file explorer, you can see within our interaction analysis results folder, there's a new folder called exports. If I open up this folder, you can see that we have a Nifty file called AD effect. Next, we're going to look at the subpopulation display. So subpopulations are going to be model-based estimates of what subjects would look like with a certain set of covariate values. So for example, if we were to pre-specify age and group membership, we can see what the corresponding subpopulation estimate would be. So the first thing I'm going to do is come over here to population, and I'm going to change this to be the subpopulation viewer. You can see that the brain disappears. This is because we have not actually specified any subpopulations yet. We can specify subpopulations over here on the top left panel. So I'm going to come down here and I'm going to click on Add New. You can see there's a new subpopulation named New Subpopulation 1. And by default, it just has the average value of age and the reference group membership. And you can see that the age is on the original scale. So you don't need to worry about applying any sort of Z transformation or anything to these values. Hint will take care of that behind the scenes. So I'm going to call this young healthy control. So you can see this has been renamed to young healthy control. And I'm going to set the age here to be 55. And I'm going to leave the group as healthy controls. And you can see that this is already filled in for us over here on the right. Then I'm going to add another group, new subpopulation. And I'm going to select this one. And I'm going to rename it to older healthy control. And click OK. And here, I'm going to take the age, and I'm going to increase it close to the maximum of what we've seen so far. So let's say 78. I'll hit enter there. So now within the image selection tool here, you can see there's this new drop-down menu that lets us choose between the different subpopulations that we've created. So right now, we've selected young healthy control, but I could also switch to older healthy control. And you can see how this part of the network has become sort of stronger here. That's due to the age effect. And you can also see that the frontal part of the network has not changed nearly as much. And that's because we did not have much of an age effect taking place in this frontal region. Now, say we were to switch from healthy controls to Alzheimer's disease patients. I'm going to go ahead and create two more subpopulations. And these are going to correspond to younger Alzheimer's disease and older Alzheimer's disease. So I'm going to start with new subpopulation 1. I'm going to set this person to be 55 years old. We're going to change the group membership to Alzheimer's disease. Let's go ahead and rename that to young AD. Similarly, let's take the second population here. Set the age to 78. And set the group membership to Alzheimer's disease. Let's also rename this to older AD. So now we have these two subpopulations defined. Let's take a look at what they look like. So first, if I pick young Alzheimer's disease, we can see we've got a very different sort of looking network here in the frontal component. So this is where we have that Alzheimer's disease effect coming in. And if I switch to the older Alzheimer's disease, you can see that this frontal part of the network has been even more wiped out. And that's due to that interaction effect that we specified between Alzheimer's disease and age. So again, if I switch back and forth, you can see younger and older. So that's an example of how you would use the subpopulation display. One last thing I want to show with the cross-sectional analysis is how we can look at the model-based estimates for specific subjects in our data set. So this can be useful for sanity checking and just for looking at sort of individual level estimates. So what I'm going to do is I'm going to go over here within the image selection, and I'm going to change from population to single subject. So we can see the map has changed just a little bit, and we now have a new drop-down menu that's letting us pick between different subjects in the data set. So if I click on this, you can see we have the choice between subject 1 all the way up to subject 30. So I'm just going to cycle through a few of these real quickly. You can see that the estimates are very similar for each subject, which is probably a good sign. But of course, they do subtly change a little bit from subject to subject due to the different values for the covariates among these subjects. So up until this point, this video has been concerned with how to do cross-sectional hierarchical ICA. So of course, in a cross-sectional analysis, we only have one visit from each subject in our data set. But of course, it's become a lot more common in recent times to collect longitudinal data on subjects. So for example, we might have visits at some scans at some baseline visit, and then we might have scans at different follow-up periods. So maybe 6 months, 1 year, so on. So of course, when we've got this sort of repeated measures data, we want to be able to incorporate that into the data. And we also want to, into the analysis, and we also want to be able to model how things like these covariate effects might be changing over time. And so that's what the longitudinal ICA approach is going to be for. So this is going to be very similar to the hierarchical ICA that we've talked about so far, but it's going to be changed just a little bit to accommodate these repeated measures on subjects. And so the main difference I want to point out in the model has to do with the second level of the model, which is where most of our focus has been. So now we say that the data for subject I at voxel V depends on their current visit, which is indexed by J. So SIJV is going to be the brain map for subject I, visit J at voxel V. We're still going to write this as a linear combination of a bunch of different terms, and it's still going to include an S0 map that represents the population average. But now we're going to add this alpha J, which is going to correspond to a visit effect, a visit J. So you can think of this as sort of like population level changes in the brain network over time. So for example, in your sample, it's possible that everybody is getting older over time, and so that would be captured by this alpha term. Then there's going to be a subject-specific random intercept. That's going to be BIV. So this is the subject-specific intercept at voxel V. And then there's going to be a set of subject-specific covariate effects, just like before. But now you're going to see that the covariate effect term, this beta term, now has a J subscript. And so what this means is that the covariate effects are going to potentially change at each different visit. So no longer will there only be one set of, say, age effects. Instead, there's an age effect at visit 1, age effect at visit 2, and so on. So that's the main way that this model differs from the cross-sectional ICA model. So it's the incorporation of this main visit effect alpha, subject-specific random intercepts, and then visit-specific covariate effects. Now, if you remember from earlier, we created a second data set that we called medication. And so this data set is what we're going to use to illustrate the longitudinal version of the toolbox. And so if you remember, if we come into the test folder here, there's the second medication data set. If we expand this, you can see that the structure of this data is very similar. We have subjects for each, for each subject, we have 3 visits. So for example, subject 12, visit 1, visit 2, and visit 3. Otherwise, this is pretty much the exact same setup as we had for the cross-sectional ICA approach. Once again, we'll get started by navigating to the hint.m file and pressing run. This is going to open up our hint toolbox, just like before. And the first step is going to be to set up our analysis folder. So I'm going to go through this one a little bit more quickly, since we went into a lot of detail for the cross-sectional analysis. And for this longitudinal analysis, I'm mainly going to point out the places that things are different from before. But first, let's go ahead and set up this analysis folder. So I'm going to click on Browse. I'm going to navigate to my desktop, and I'm going to create a new folder called Tutorial Medication. And I'll just press Open. And so now our analysis folder is set up. Next, we need to read in the NIfTI data. We're going to click on Load Data, just like we did for the cross-sectional analysis. But this time, we need to change the analysis type. So instead of cross-sectional, we're going to come down here and we're going to click on Longitudinal. There's going to be a blank over here on the right asking us how many visits there are. And so it's important that you put in the correct number of visits here. So for this data, we have 3 visits per subject. So I'm going to change this 1 to a 3. Then we're going to load the mask and the covariate file just as we did before. So I'm going to come over here to medication, scroll down until I find the mask, and select that. I'm going to do the same thing for the covariate file. So I have the medication data covariates, and I'm going to open this. You can see that the total number of files found was 90, which matches what we would expect since we had 30 subjects, each with 3 visits. So I'm going to click Continue and OK. And so now the data has successfully loaded. So one important thing to notice before we move on is how the covariate file should be set up for a longitudinal data analysis. So if I come into the medication folder and I open up the medication covariates.csv file, we can see how this looks. And so right away, you'll notice that this is basically exactly the same as the Alzheimer's disease data set that we did before. The main difference is when you have a longitudinal study, not only is the first column corresponding to file paths for the NIfTI files, but actually the first J columns are, where J is the number of visits. So column 1 is visit 1, column 2 is visit 2, column 3 is visit 3, and so on. And then just like before, the remaining columns are going to be the covariate values. So we have age, group, and medication type here. Next, let's go ahead and set up the model specification. So I'm going to click on model specification here. You can see that this works exactly the same as it did in the cross-sectional case. So we have the age here, which is already normalized for us. And then we have the effects coded covariate values for our two different categorical covariates. So we have the group. So this is that treatment type. It's either going to be control, traditional, or novel. And then we also have the medication type, which is either going to be capsule, injection, or powder. So there's no changes that we need to make here. So we're just going to leave this as it is and move on. So I'm going to come down here and click on OK. For the number of PCs and the number of ICs, I'm going to set this the same as before. So we generated data with 3 ICs. I'm going to use 3. And then I'm going to double that to give us 6 principal components. Then I can go ahead and click on PCA dimension reduction. There's 90 subjects that need to have their PCA performed here. So this is going to take just a few minutes. I'm going to pause the recording and then I'll resume it when it's done. Okay, we can see that the progress bar is now filled in and the PCA is done running. So just like before, we're now ready to generate an initial guess. So I'm going to go ahead and click on this button. The guess is now done. And the last thing we need to do is preview our population level components just to make sure that they make sense. So once again, I'll click on this button. The viewer will open. We've got our visual network here. We've got a sensory motor network up here. And then finally, we have our default mode network once again. So these all look good. I'm going to go ahead and close this out. I'm going to click on Save, Setup, and Continue. It's going to ask me to input a prefix, and I'm just going to call this analysis 1. It's now creating that run info file, and now it's automatically going to take us to the second panel. Once again, we can do the EM algorithm just using the default settings. So I'm going to leave the number of iterations at 100. I'm going to leave the tuning parameters at the same value for the convergence, and then I'm going to click on Run. Okay, the algorithm has now finished running, and we are ready to move on to displaying our results. So I'm going to go ahead and click on this. We can see that once again, we've moved to the Visualization tab, and the prefix and display path have already been filled out for us, which means we're ready to click on Display and view the longitudinal findings. Viewing the results for a longitudinal analysis is very similar to viewing the results under a cross-sectional analysis. But one of the main differences is going to be that now we're also going to have this sort of visit dimension to consider. So one thing you'll notice is that the trajectories panel now has some values populated to it. So right now, after just opening up the window, we're looking at the population level viewer, and you can see that there is a population average that is varying by visit here. Of course, if we look at the y-axis, we can see that it's not actually changing a whole lot. And the values that are within this sort of trajectory viewer will change to reflect wherever we're clicking in the brain. So you can see as I click around, this is changing just a little bit. And of course, if I click within the actually active region of the brain, this increases quite a bit. We can also see how this works with the covariate effect viewer. So I've switched here to the default mode network, which is the one that I showed in the slides at the beginning when we were generating data for the longitudinal study. And so I'm going to switch from the population viewer to the covariate effect viewer. And I'm going to switch to our novel treatment group. So at visit 1, you can see that there's a bit of an effect here at the voxel that I have selected. If I jump up to visit 2, you start to see that effect a little bit more strongly. And then finally at visit 3, we can see the effect very strongly. And so that's also reflected in this trajectory viewer for the covariate effects. So we can see that this covariate effect for the novel treatment group has a time varying effect on the brain network. It's strongest at time point 3 and weakest at time point 1. One thing that we can do that will show this quite clearly is to look at the contrast of the novel treatment group at visit 3 versus the novel treatment group at visit 1. So we can do this by coming over to the linear combinations setting over here. So I'm going to click on linear combinations, and I'm going to click on add new. And I'm going to rename this to be novel 3 versus novel 1. So I'm going to leave, this starts by default with the coefficient being 0 for every effect in the model. I'm going to come find the novel effect at visit 3. I'm going to set that to 1 for the coefficient. And then I'm going to find the novel treatment effect at visit 1. And I'm going to set this to be -1. And so this is going to show us the covariate effect estimate for visit 3 versus visit 1. I can come over here to the image selection, change this to linear combination, and it's going to go ahead and show us 3 versus 1. And it looks about like we would expect. We can see this strong region right here in the center, and everything else is quite weak. And of course, we can threshold this just like before. So I'm going to threshold this at, let's say, 2.0. And we can see the surviving regions. So there's this very strong cluster in this sort of lateral region of the default mode. One last feature of the hint toolbox that I want to mention is that all of the analyses can be carried out via a script instead of using the GUI interface. And so this is useful if you have a very large data set that might take a long time to run, or if you want to run the estimation procedure, say, using a cluster. And it's very simple to do this. So for both of the examples that we did today, the cross-sectional analysis and the longitudinal analysis, the hint toolbox comes built in under the test folder with script versions of those analyses, which you can then modify for whatever analysis data that you have that you might want to work with. So I'll open up the cross-sectional analysis, for example. You can see it's very simple to run these analyses via a script. All you have to do is specify the path where the data is stored, specify the path where you want to read in the data from, specify the locations for your covariate, your mask, and your output directory, and then you just run the hint analysis. So this is very simple in practice. And you can look up this function to find out exactly what each argument is, but it's basically the same things that we filled out when we were using the GUI version. So this, again, is very useful if you want to, say, run this analysis on a cluster. So that about wraps up this tutorial for how to use the 2.0 release of the hint toolbox. I've got a few different references on the screen here for showing some of these different hierarchical ICA approaches. And in particular, if you're going to be using the cross-sectional version of the toolbox, the Xian Guo 2016 reference introduces that. And for the longitudinal version of the toolbox, this paper from 2019 in NeuroImage introduces that version. So please reference either of those papers if you're interested in learning more about how the approaches work.